Hi, in the design analysis of algorithm classes, as a part of the exam 1, I am going to demonstrate dividing master method. The context of my demonstration is related to recurrence relations. So what is a recurrence relation? It is a recursively defined sequence. So basically, whenever we have a recursively defined sequence, that is defined by recurrence relation mathematically. For example, we have an arithmetic progression like that, a plus d, a plus 2d, and so on. So we can definitely represent it as a recurrence relation. Now, in the current context of the design and algorithm, I'm going to show you some examples and some processes of problem solving, particularly emphasizing on divide and conquer method. So what is that method? It's basically we take a large problem and divide it into smaller sub problems until the time reaches when the problem becomes trivial. So the way we do it is that we divide it and then combine parts to create a solution. Let's try to give an example from binary search algorithm. So you see here the pseudocode for the binary search algorithm. So input is an ordered array, and then the low is the lowest index of the array, high is the highest index of the array, and x is some number that you wish to find. So as you see in the illustration on the right hand side, there are numbers like 2, 3, 5, 7, 9, 10, 11, 12. So this is an ordered array, and the midpoint is at 7, the low point is at 2, high point is at 12. So if we go through the algorithm, we can see the first line, second line. I mean first line is quite trivial. It gives you a constant time complexity. Then at the mid, we determine the midpoint by by adding low and high and then divide it by 2. So this also contributes to a constant time complexity. And then if x equals the midpoint, the number at the midpoint, then we return true. This also gives you a constant current time complexity. But then what you find is that if x is less than the number at the midpoint, then we recursively call binary search. And also in the next line, if x is greater than a at the midpoint, then we call the same function with different inputs. So in a given situation, only one of these binary search is called recursively. Either x less than a, for a given x, it either satisfies less than a midpoint or greater than a midpoint. So that's all about the algorithm. In each step, we are we are dividing the number, the length by 2, and we look for the uh, number that we are trying to find. So in the language of design and algorithm analysis, we're not trying to describe the algorithm here, we are trying to analyze the algorithm here. So in the in essence of the algorithm analysis for recurrence relations, the scenario that we described before in the illustration of the binary search, we can represent it as a simple function like Tn equals a times Tn by b, plus f as a function of n, when fn has the complexity of n to the power k log to the power p n. So basically what I've tried to say here, in this generalized form of relation, there are two variables, a and b, both of them more than equals 1. These are the constants of these parameters. So a is typically the number of subproblems. So in the binary search, what is the number of subproblems? It's just 1. And then n by b is the size of the subproblem solved. B is how many divisions we are making in each step. So in our case, it is 2. And Fn is the steps needed to split subproblems and combine solutions to subproblems. In case of binary search, it is just a constant. Now, there are three ways to find the time complexity of this type of relationship. Number one is by doing the algebraic steps, recursion and substitution. Number two is the recursion tree, solving a recursion tree. And number three is the master method, which is the center point of our today's presentation. So the master method, what it is, it's a generalized method that is used, that can be applied to solve the recurrence relations uh, arising in divide and conquer algorithms. So we should focus within the realm of master method. We should focus on two variables, log base ba and k. So k, you can see from the equation above, for tn and fn, you can see b and a and k. According to master's method, there are three cases as illustrated in the right hand side picture. The case one, when log ba is greater than a, that means it's a left dominant, then we have a complexity of O, big O, n to the power of log ba. The case 2 is if none of them are dominants, log ba equals k, then there are three situations according to the value of p. If p greater than 1, then we have time complexity O n to the power k log p plus 1 n. If p equals -1, then we have O n to the power k log n. And if p less than -1, then O n to the power k. Case 3 is the situation when log ba less than k, that is the right dominant. In that case, it's much more straightforward. If p greater than equals 0, then n to the power k log pn, and p less than equals 0, then log term is not important anymore. So we have O n to the power k. So let's apply master's method to binary search. So I have reiterated binary search algorithm again in this slide, but you can see there are three markers, 1, 2, and 3. 1 contributes to, it basically shows the division for the divide and conquer algorithm. The division, it is divided by 2. The array is divided by 2 for divide and conquer. And step number 2 and 3 illustrates the different situations to find x. Remember, in a given recursion, only 2 or 3 will be applied. So what will be the number of the number for the a? So a should be 1 in this case. But then what is the number of divisions? That is b, that is 2. Then we have fn, which is the constant. So in this case, we can see, if we take a look at the Master's theorem, k equals 0, p equals 0. So log AB equals 0, which is equals k. That means this is the second case of Master's theorem, and we can get O of log n, time complexity. And if we apply other two methods like the substitution and recursion trees, we can show, we are not showing here, but we can show that we can derive the same conclusion on the time complexity, that is O log n. Let's illustrate another example for a different case. Let's put an arbitrary algorithm here, the time complexity Tn equals that's the time function for another algorithm. This is equal to 7 Tn by 2 n cube plus n cube log n. So the recursive function here is the left one, where we can find a equals 7, b equals 2, k equals 3, and also p equals -1. So then we can find log BA equals log 27, which is less than log 28. It's just mathematical trick. So we can conclude here that log BA less than K. That means we have case 3. And with P equals -1, it goes to case 3, second case, which is O log n to the power K. So the complexity should be O n cube in this case, n to the power 3 in this case. So in this way, we have shown that master method gives you a straightforward way to solve the problem of recursions. Uh, Typically for the recursive divide algorithm, this form of the master theorem is applicable for divide and conquer algorithm. And in this way, if we can have a divisive recursion function, we can apply the master theorem to get the time complexity, to derive the time complexity for those relations. Hope this illustration helped you to understand the master's method and its applicabilities. Thank you.